Ever looked at a skyscraper, a bridge, or even a simple sidewalk and wondered what holds it all together? The answer is cement. And behind that plain gray powder is a powerful high-temperature transformation process that turns raw rock into the backbone of modern construction. Let's take a comprehensive, engaging, and in-depth look at how cement is made, step by step, inside a factory. The journey of cement begins in quarries, where raw materials are sourced from the earth. The most important ingredient is limestone, a rock rich in calcium carbonate. Along with limestone, other materials such as clay, shale, sand, and iron ore are also required. These materials supply essential elements like silica, alumina, and iron, which are crucial for forming cement compounds. Workers use heavy machinery and controlled blasting to break large sections of rock from the quarry walls. Once extracted, these raw materials are transported to the cement plant. Massive dump trucks, conveyor belts, or rail systems carry the rocks to the next stage. Before anything else can happen, the rocks must be reduced in size. This brings us to the crushing stage. Large crushers break down huge chunks of rock into smaller pieces, typically no larger than a few centimeters. This makes them easier to handle and process further. After crushing, the materials are carefully blended. This step is extremely important because the quality of the cement depends on a precise chemical composition. Advanced sensors and computer systems analyze the materials and adjust proportions to maintain consistency. The goal is to create a uniform mixture that contains the right balance of all required elements. Next comes the raw grinding stage. The blended materials are fed into large rotating mills known as raw mills. Inside, heavy steel balls or rollers grind the mixture into a very fine powder called raw meal. The fineness of this powder is critical because it ensures efficient chemical reactions in later stages. The finer the particles, the better they react when heated. Once the raw meal is prepared, it moves to the preheating stage. This step improves energy efficiency and prepares the material for the intense heat of the kiln. The raw meal passes through a series of cyclone preheaters where it is exposed to hot gases coming from the kiln below. As the temperature rises, moisture is removed, and some initial chemical changes begin. This stage helps reduce the energy needed in the kiln. After preheating, the material enters the most important part of the process, the rotary kiln. This massive cylindrical furnace is slightly tilted and rotates slowly. It can be over 100 meters long and operates at temperatures reaching around 1450 degrees C. As the raw meal travels through the kiln, it undergoes a series of complex chemical reactions. One of the key reactions is calcination, where calcium carbonate in limestone breaks down into calcium oxide and carbon dioxide. As the temperature increases further, the materials begin to react and partially melt. This leads to the formation of new compounds such as tricalcium silicate and dicalcium silicate, which are responsible for cement's strength. At the hottest point in the kiln, the material forms small, dark gray nodules known as clinker. These clinker nodules are the core product of the cement-making process. They look like small pebbles, but contain all the essential compounds needed to produce cement. When the clinker exits the kiln, it is extremely hot, often over 1000 degrees C. It must be cooled rapidly to preserve its structure and quality. This is done in the cooling stage, where powerful fans blow air over the clinker. Rapid cooling also helps recover heat, which can be reused in the process, improving overall efficiency. Once cooled, the clinker is ready for the final transformation. However, it cannot be used directly as cement yet. It must first be finely ground. In the final grinding stage, clinker is mixed with a small amount of gypsum. Gypsum plays an important role by controlling the setting time of cement, preventing it from hardening too quickly when mixed with water. This mixture is fed into cement mills, where it is ground into an extremely fine powder. The result is the cement we recognize. The fineness of the powder is carefully controlled because it affects how the cement behaves when used in construction. Finer cement reacts faster with water and can develop strength more quickly. Before the cement is ready for use, it undergoes strict quality control testing. Samples are taken and tested for properties such as strength, setting time, and chemical composition. Laboratories within the plant ensure that the cement meets industry standards. Any variation can impact the performance of concrete, so precision is essential. After passing quality checks, the cement is stored in large silos. These silos protect it from moisture and contamination. Cement is highly sensitive to water, so keeping it dry is critical. From the silos, it is either packed into bags or transported in bulk using tankers, trains, or ships. Packaging is another important step. Cement is typically packed in strong paper bags or supplied in bulk for large construction projects. Efficient packaging ensures easy handling, transportation, and storage. From here, the cement is distributed to construction sites, hardware stores, and infrastructure projects around the world. One fascinating aspect of cement production is its scale. Large cement plants can produce thousands of tons of cement every day. The entire process runs continuously, with materials constantly moving through each stage. Despite this scale, precision and control remain key to maintaining quality. Energy consumption is a major factor in cement manufacturing. The high temperatures required in the kiln demand a significant amount of fuel. To address this, many modern plants use alternative fuels such as industrial waste, biomass, and recycled materials. This helps reduce reliance on traditional fossil fuels. Environmental impact is another important consideration. Cement production is a significant source of carbon dioxide emissions, both from fuel combustion and from chemical reactions in the kiln. As a result, the industry is actively exploring more sustainable practices. These include improving energy efficiency, using alternative raw materials, and developing carbon capture technologies. Automation and technology play a major role in modern cement plants. Sensors, control systems, and advanced software monitor every stage of production. From raw material blending to kiln operation and final grinding, everything is carefully controlled to ensure optimal performance. This not only improves efficiency, but also enhances safety and consistency. Another interesting detail is how nothing goes to waste. Dust collected during the process is often recycled back into production. Heat generated in one stage is reused in another. This level of efficiency helps make the process more sustainable and cost-effective. Cement is incredibly versatile and forms the foundation of concrete, which is one of the most widely used materials in the world. When mixed with water, sand, and aggregates, cement acts as a binder that holds everything together. This simple yet powerful property is what makes it essential for construction. The entire journey from raw rock to finished cement is a remarkable example of industrial engineering. It combines natural resources, high temperatures, precise chemistry, and advanced machinery into a seamless process. Each step plays a critical role in ensuring that the final product is strong, reliable, and ready for use. So the next time you walk past a construction site or see a towering building, remember the incredible journey behind the cement that holds it together. What looks like ordinary gray powder is actually the result of an intense and carefully controlled process that transforms raw materials into something that shapes the modern world. If you enjoyed this deep and engaging breakdown, don't forget to like, subscribe, and drop a comment on what process you want to explore next.